your homework here. Quiz grade should be in. I just we got a couple of people to make that up. Yep. So we'll get that done, and then we can hopefully take a look at it. So on any of the ones we've talked about, 1 through 9, and I know that could be a decent amount of questions here, so we're really going to talk a lot today about the process here of this U substitution, doing the antiderivatives. The next thing we have grade-wise is the gateway test on antiderivatives, and that is going to be, I think, next Thursday is kind of what it looks like. Okay, and that gives us today to go through more of this U substitution. This is really a big one. I mean, this is the chain rule in reverse. Basically, this is how you deal with functions that have something kind of on the inside. There are chain rules involved. But if you think about chain rule, is almost always involved in derivatives. There almost always seems to be something on the inside of a function that we're dealing with. And so this is kind of how we have to handle those. So this is a big one. There are some other ones that we won't get into, some other types of antiderivative techniques that we can get into how to. That we won't get into, but we're going to do one other one, which is kind of a product rule in reverse kind of thing, and that is called integration by parts. We'll get into that on Monday, and then there's a lot of practice coming. A lot of. I mean, you just need a lot of practice because antiderivatives. Think about antiderivatives. One of the quotes I've seen about it in a textbook that I always liked was it's a little more of an art than a science. In other words, derivatives are more like follow the rules, okay? A little more of the kind of the left brain kind of, okay, here's all this page of rules and it looks like this, do this, follow these steps, and there you go, and there's the derivative. Okay, so if you like that kind of thing, you like derivatives. So that's more of the science. And then the art of the antiderivatives is more a recognition of, again, kind of what it looks like, but it's more of a guess and check. It's more of a trying things, kind of seeing it in reverse kind of a thing. And so it's not quite the same. The goal of all of the techniques, and that's why we call them typically antiderivative techniques, not really antiderivative rules. The goal of all of the techniques for antiderivatives is to reduce the function or the integral down to page 333, right? Remember on page 333 the other day we had that little table of basic antiderivatives? That's really what you need to memorize. You need to know those, which are just some of the basic derivative rules in reverse. And so what we're trying to do is reduce a complex kind of integral down to one of those. And then you just do the antiderivative and then go from there, depending on the technique. Okay, so that's kind of the idea. All right, so if we look at where we've been with this, just kind of to where we got to this point. Of course, we started with fundamental theorem part 1, which just said this. So we're starting with area, right? So the whole idea was area, and then we're hoping as we get into chapter 6 and chapter 7, we can do chapter 6 more about defining what the area function is. Well, actually, the end of chapter 5 here will be defining area, an infinite, how we actually get an area into this. We've already realized it's antiderivative. To be honest, see, this is one of those things our textbook does differently than almost every other calculus textbook, which I like. I mean, years ago when I first went to this textbook, I had a student who was getting tutored who had a family friend was a math professor at UNK, head of the math department. And actually a friend of mine because my wife played softball at UNK and she knew, it was a math major there, so she knew all these professors. So anyway, he came to me one day and he says, well, I'm helping so-and-so. They're coming to me for some help. I said, oh, okay. And it hurt my feelings at all. I don't know why they're coming to me, but whatever, okay. Must be because professor is way smart. But anyway, he came to me, he says, and she showed me, she's doing these antiderivatives, and because we talked about antiderivatives, back in chapter 2, right? As soon as we learned about derivatives, we talked about antiderivatives. We talked about going in reverse. So I think that's what they're working on. And You haven't even done integrals yet. You haven't even done like rectangles under the curve, and you haven't even done, which every other book would do first, and then bring in antiderivative. How can you do that? I explained to him kind of he's out of his phrases. But anyway, so this is pretty non-traditional. But what we're going to do, so we haven't really defined area. Remember when we did the rectangles? We talked about rectangles, under the curve. We even had that little calculator program where we tried 20 rectangles. Anybody remember that way back when, like the third day of class? 20, and then some of you said, well, I'll try 10,000. Your calculator froze up, right? Remember that? Okay, so if 20 rectangles is a pretty good approximation, then 100 must be good, and 1,000 must be good. What are we going to do? Well, it's an infinite number, right? Well, that's what we're going to get to that yet. But usually they start talking about integrals with that. This book doesn't do it. We go into antiderivatives and all that stuff first. Okay, for you guys, that doesn't really matter. I just think conceptually it helps understanding when this is all said and done. I think this is a better way to approach it. But anyway, what's happening here is we've said, okay, area under the curve, it might be interesting. Got a velocity curve, do the area under it, you get distance. Okay, we talked about the average value of the function, how that seems to make sense. Okay, so we've talked about a couple of things. All right, so we introduced this thing of an area function, and lo and behold, when we actually started looking at it from kind of an equation perspective, we realized, oh my God, it's the antiderivative. Look at that. It's the derivative in reverse. So we got this sense from this that the antiderivative might be involved somehow. So then we went into the thing with the trapezoids and all that, and we came up with this. And oh, wow, it is involved. And not only is it involved, but all you need to do is do the antiderivative and then plug this number in, plug this number in, and that will give you any area under a curve as long as it has an antiderivative. Okay, so then it comes to, be that, so being able to do an antiderivative might be of use. If finding areas is possibly of some use, and that's what chapter 7 will be about, is showing you some of those uses of doing integrals. So if that might be some use, and the best way to find those areas is to do an antiderivative, then maybe it would be worth our time to be able to do some antiderivatives. Okay, so that's why we are where we are right now. We need to figure out how to do antiderivatives of a variety of different functions so we can do this. That's the idea. Okay? All right. So then we talked about this. Okay, so where we all started with this was being able to find a fixed piece of area. So geometry, we can do that, but that doesn't happen very often. This is the big one. And then, of course, chapter 6 is going to be about, okay, but if finding areas is of use to us, how do we handle those functions that don't have an antiderivative? That's when we'll learn about this. Okay, so kind of big picture of what's going on. All right, so for now though, let's focus in on this and say, okay, finding big F might be a thing, right? Might be something we might want to do. Okay, so then we talked about our area functions. You have a fixed piece of area. Okay, if you get a free initial condition, that's going to be a specific antiderivative. And then if you get this, we're just going to call that an indefinite integral, and that's just going to be your general antiderivative, and that's what we're going to be working on here. Okay? All right, so homework questions. 10. Before 10.
Yeah.
Number, okay. Well, why not? Right? Why not? Okay? So we, and I get it, because I gave you a quick little preview right before we were, focused on the quiz and all that, and so I understand. So number 1 says 4x plus 3 to the negative third dx, right? Like that. And they tell you what to pick for u. Now enjoy that on those first few problems, because that's the last time that's going to happen, right? You've got to figure out what to pick for u. This is called u substitution. Okay? Now, they told you to let u equal 4x plus 3. Now that's the inside. That's often what we let u be. Now the next step I said was we now want to do what? The derivative. That's du over dx, which is 4. Then we said we're going to take this dx and we're going to stick it over there. Okay? Now I do that every single time. So I'm going to do that for a few of them today, and then I'm going to quit doing this middle step, and I'm just going to skip right to this. And you're going to hear me say, what's du? And when you think du, think derivative of u. And then on the other side, we'll always stick on a dx at the end. Why? Because of this step right here, right? Okay. Anyway, and I encourage you to show your work exactly the way I'm doing it here. Now, You don't want to, that's fine. You're on your own. If you figure it out, if it's working for you, that's great. But I think they should look like this almost every time. Over here, I put this work, draw myself a little arrow. I am now going to create myself a new integral, but that new integral is going to have u's, not x's. So I'm going to sub. So what does that mean? Well, it means I'm going to take that, I'm going to replace it with what? U to the -3, right? Because u is equal to 4x plus 3. But I also have to sub out the dx. See, it's like the basketball team where I'm taking out the starters and putting a new group in, right? The starters are second. I'm gonna put 5 new ones in. I'm not gonna leave even one. Not even one. I can't mix u's with x's, okay? So I've got, I'm taking that out. I've also got to take out the dx. Well, what's dx equal to? Well, there's just 4 here. Well, let's move it over. That's perfectly legal. So we're gonna divide that over there. So now we can see that dx is equal to 1/4 du. So I can take the dx out and I can replace it with a 1/4 and a du. Now, why did I write them there? It doesn't really matter, but with constants, we've talked about how you pull it outside the integral. I'd rather have it out there. The du always goes at the end. The dx and du always goes at the end of an integral. All right. So now, look what I did. I just changed that integral into something that looks like page 333. It's just a simple power. Just a simple power. So I raise the power up 1, which is -2. The 1/4 just sits there. And then I divide by that new power, -2. And then I tack on a plus c. Now the question I often get from people is, what happened to the integral symbol? What happened to the du? Where did they go? What's the answer to that? Yeah, those were just there to tell me to do the antiderivative with respect to u. And some of us were talking right before class started. If I gave you this problem right here and said, what's the answer to that? What would you say? 3x squared. But I don't remember anybody ever saying, well, what happened to the d? What happened to the dx? Right? I don't remember anybody ever thinking that, right? Why? Because they were just there to tell me to do the derivative with respect to x. So I did it, and then those are gone. So that's what this symbol is and this symbol. This is saying do the antiderivative with respect to u, and so we do it, and then they go away. They're not there. And so this would be -1/8 u to the -2 plus c, and then we got to take and put it back into our u's. So we're going to put 4x plus 3 back in there. And so we got -1/8. Thought my wife would finally come through. All right, 4x plus 3 to the -2 plus c, right? Like that. All right, and now you're back in x's. Now, to be honest, for that one, I wouldn't expect you to go through all that, right? For this one, because there's just a 4 on the inside, don't you already know you're going to kick out a what? 1/4. So to be honest, if this one was on the gateway test, I would almost think you would just look at that and say, oh, this is just a 4 on the inside. This is just a power rule. I'm going to raise that up to -2, divide by -2, kick out a 1/4. That's going to give me my -1/8. So I don't even think you needed to do u substitution on this one, right? But it works, just to show you it works, okay? That's where it comes from, all right? So then the question could be, let's just do what I was doing with those guys earlier. Well, we did 3. Let's skip that one and let's do another one. Let's do any of them. I don't care. Somebody got one? I know you said 10. Let's try another one. Before 10. 10 is a little tricky. 7? Okay. So 7 says the integral of e to the 1/x over x squared dx, like that, right? And they tell you to let u equal 1/x. Now, why would you do that? Well, it's the inside. That's almost always the first thing you choose for u. Okay, now as we go through these, I'll get a little more specific about your strategy for picking your u, or why that was a good choice for you. But right now, we'll just let u equal the inside, which is 1/x, or x to the -1. Why do I want to write it x to the -1? Because what am I about to do? The derivative, right? Now, this is another thing that sometimes gets people when we're doing antiderivatives, is in the middle of the problem, you're doing a derivative. So sometimes we get the rules mixed up, right? So just remember, your derivative rules, and at the end come the antiderivative, okay? So we're going to do du over dx. I'm going to do it one more time. I'm going to write it this way. Then I'm going to start skipping this middle step. So that's -1 x to the -2. So you bring down the -1 like that. Okay? Now I'm going to move the dx over. Now, what you're going to find is how you write these things is really important to how well you can understand and see this. Because I see an x to the negative 2 there, but there's not an x to the negative 2 up there, but yes, there is, right? It's there. It's on the bottom, okay? So what I actually would rather do on this one is I'm going to write this negative 1 over x squared dx like that. Okay, now I'm going to come over here and I'm going to say, all right, new integral. All right, let's start subbing stuff out. Okay, so that's going to be e to the u, right? So that's taken care of. Now, I look down here and I look up here and look at this right here. What is that? And don't say x squared dx. That is not x squared dx. That's what? It's 1 over x squared dx, right? This right here is 1 over x squared dx, which isn't that what I have here except for the negative. Well, I can just divide both sides by a negative, right? And I can get that over there. So look what you got. You got 1 over x squared dx right here, and you got 1 over x squared dx right here. So that can be replaced with a negative and a du. And look what happened. It's now a simple antiderivative right from page 333. Okay, so the antiderivative of e to the u is e to the u, the negative stays there, plus c, and now we put our 1 over x back in, negative e to the 1 over x plus c. Okay, and that's our answer. And you can check it with the derivative. So the derivative of this would be what? It would, right, the derivative of this, if this was the derivative gateway test, we would have written this negative e to the x to the negative 1, and we'd say, okay, that's negative e x to the negative 1 times the derivative of the inside. Well, what's the derivative of x to the negative 1? It's negative 1 x to the negative 2. Well, sure enough, those two negatives would cancel. That would flip to the bottom, and we'd have e to the 1 over x with an x squared on the bottom, which is that right there. Okay? All right, now let's talk about this a minute. Why did that work so nicely? The reason, so when you're picking something for you, okay, and you think about what we did, this process over here. So when you're looking at an integral and thinking about, is this going to be u substitution? Number one, the answer to that's usually yes, because it's the main technique we're going to learn about, okay? So it's almost always going to be, yeah, there's something I can pick for a u. And so you're going to look at this, you're going to say, well, in the first place, I should probably look to the inside. So the thought process is this. If I let u be the 1 over x, what's the du? That's always the question. So with u substitution, you're always trying to think a step ahead. So you say, okay, if I pick u to be 1 over x, that's x to the negative 1, the du will be negative 1 x to the negative 2. I don't really care about the negative 1, but I'll have an x to the negative 2. Oh, that's an x squared on the bottom. Oh, look at that. It's sitting right there. So I'm always thinking to myself, if I pick this u, will the du be setting in there somewhere? And if it is, that's going to be good. And that's probably going to be what I want to do. And then you go down that road. Okay? All right, so let's go to number 10. So number 10. So this is, well, it's not too early, but so this is one of those where you say, okay, we were just talking about picking something on the inside. We're talking about picking something on the inside. Well, there is no real inside here, okay? So the second thing you often look for is let u be the bottom. Let u be the bottom, okay? So that's what they told us to do here. They said let u equal 1 over 1 plus x. Okay, so what's the du? Now, I'm going to skip that middle step, right? My dx is already going to go over to the other side. So what's the derivative here? 1 and then dx, right? You put the 1, you don't have to put the 1, right? Just be 1 and then there'd be a dx there, right? I'm just skipping this step right here, right? Du dx equals 1 and then move the dx over. Okay, so du equals dx. Okay, so now my new integral, that is going to get replaced with u. And that is going to get replaced by du, which I always want to put over there, right? So the dx got replaced by du, and the 1 plus x got replaced by u, but there's still that leftover x. And we don't want to mix x's and u's, so I can't just stick an x there, okay? So this is a common situation, and it's very much this same situation, which there's leftover x or leftover x's. Okay, well, what do you do if there's leftover x's? Anybody got a thought? Yeah, you can come up to this thing, just like over here we took and divided this negative over, we divided this 4 over. Right up here, we can subtract 1. So u minus 1 is going to be equivalent to x. So we can now put the u minus 1 right here. Okay? All right. So, once we do that, though, now, if you're kind of with it here and following along, you'd be thinking, well, that didn't seem to do much. Because, the whole goal was to turn this into something that looks like page 333, some simple antiderivative. Looks to me like we just kind of flipped this over. And it almost looks like it didn't get us anywhere, but in reality it did. What did this do for us? What makes this fraction better than the first one? Well, why? It's an algebra answer. It's an algebra thing. Why that blue one's better? Say it again. One variable where, though? There's a single denominator. What can we do with a fraction that has a single denominator? Break it apart. That's the key. So this is why we often let u be the bottom. If the bottom is some messy stuff, if we let u be the bottom, our new integral will just have a u down there, and it'll be a single denominator, which means we can split it apart. So having a messy top with a single denominator is always better than the reverse. Okay, and that's why we do it. So now what we can do is we can split this into, and I won't always show all these steps, but right now I will, since this is the first one we've done. So we can split it into that. Remember, you never want to split a denominator, but you could split a fraction over a single denominator. So you can split the top up all over that single denominator. So now this becomes 1 minus 1 over u du. Now, usually I would skip this step and just go right to this step. Well, now we can do that because we have the rule with antiderivatives which says we can do this antiderivative, then do this antiderivative. I can split it into 2 intervals, but we don't really need to. So what's the antiderivative of 1? No, careful. With respect to u, it's u minus, what's the antiderivative of 1 over u? ln u, and you got to put bars around it. We always put bars around it when we do this, but ln u just have to, right? We talked about that because u could be negative in this problem. There's no restriction here for u not to be negative. U can't be 0, but u could be negative, and you can't do natural log of the negative, so we need to put bars around it. Okay, and then plus c. Now we put our x plus 1 back in. Okay, so now we get x plus 1 minus ln x plus 1 plus c. Right? Okay, get your calculators out. And do this one. Just type the original problem. Now, I don't know that we've done this before on the calculator. Maybe we have. You might remember when we've done the integrals on our calculator, there's 2 different integrals there. There's the one with the 2 boxes for the a and the b. And then there's also the integral symbol without the 2 boxes. That's the one you want to pick here. So some of you have asked me, is there a key here to do an antiderivative? That's it, the indefinite integral symbol. So the one without the a and the b. So go ahead and do the integral of x over 1 plus x dx and see if you get the same thing we got there. Daniel, what you're saying?
Mine says x minus ln x plus 1.
Does it have the bars around it?
Yeah.
It doesn't. So the calculator doesn't put a plus c on it for us, right? Calculator doesn't put a plus c, but it's missing what? It's missing the 1. So what did we do wrong? Well, plus c could be anything, but you're on the right track. No. What happened to the 1? What's 1 plus c? It's just another constant. So what can we call it? D. D? No, we just call it c. 1 plus c, this is weird, but 1 plus c, in context of these problems, 1 plus c is c. 1 plus c is c. Because c is just some constant. So 1 plus c is just some other constant, right? I mean, so it doesn't matter. So what happens is the 1 just gets absorbed into the c. Okay, now if you left it like this on the gateway test, I don't think that I would take points on. But just understand when you look at it on your calculator, that's what's going on. They're just saying, well, that 1's just a constant added to another arbitrary constant, it's just some other arbitrary constant. Okay? All right. So but that's why the calculator does that. So actually, if somebody right here, if you would have said the antiderivative of 1 and you'd have put x, right, as some of you were saying instead of u, it had turned out you'd have been right. But that's a little bit lucky because that u could have been something else. Now let me talk about natural log here a minute because I think somebody brought it up the other day. But if I ask you to do this problem, if I ask you to do this antiderivative right here, is that going to be an ln? Is that going to be a natural log? That is not a natural log. That's x to the negative 2, and we do the antiderivative. We raise it up 1, which would be negative 1 divided by negative 1. Only x to the first is on the bottom is going to be a natural log. Only a 1 over u. Not a 1 over u squared, not a 1 over u cubed, not a 1 over u to the 1/2. Those are all power rule. Only 1 over u to the first. Why? Because u to the negative 1, if you raise the power up 1, that's 0 divided by, if you did a power rule on u to the negative 1, what would you get? U to the 0 divided by 0, which you can't do, right? So u to the negative 1, you cannot do a power rule on, right? And that's why it's ln. So that's the only time. So be careful of that because people sometimes will do that. Like if we have a 1 plus x quantity squared here, sometimes we have that. Well, then we might let u just be the 1 plus x on the inside, not the whole bottom. We'll let it be the inside. And then the bottom will be u squared. That's not going to be an ln. Okay, so be careful with that. All right, any others? Anybody get far enough to have questions on any of the other ones? Where they didn't tell you? Dan.
43.
Tell me the problem.
Two x plus 3 over x squared plus 3x plus 5, all raised to the 4th.
Like that?
Yep.
And the bottom's all to the 4th?
Yes.
Right? Like that. Okay? All right, so now, with everything that we've talked about, what do you suppose you would pick for the u? Excellent. I just kind of talked about it. You pick the inside of the function, which happens to be in the bottom. The inside of the bottom. But again, because the thought process should be this. We let u be the inside, the x squared plus 3x plus 5, because what's the du? 2x plus 3, right? The derivative of this is 2x plus 3 dx, which is setting right up there. And so that's going to be a nice substitution. So that's the thought process. So when you hear me say, oh, this is a, like sometimes we go through the packets and stuff and you see one and say, hey, this is a great substitution one. Why do I know it's a great substitution one? Because I'm thinking a couple steps ahead. If I let u be this, then the du will be this, which is setting right there. It'll all be good. All right, then you'll have to mess with a few fractions maybe or something, but you can get there. All right, so yes, we let u equal x squared plus 3x plus 5. The du, the derivative is 2x plus 3, and there'll be a dx there because I brought it over, right, in the invisible step that I'm skipping. And then we say, okay, what's our new integral? So our new integral, we're going to take all of that bottom and make that u to the 4th, right, because that's my u. The du is all right there, so I'm going to put that over there, which means I got a 1 there. So look at that. With that substitution idea, we've turned that into a simple u to the negative 4, which I can now just raise up 1, which is u to the negative 3, divide by negative 3, which would be that, right? Because we know we'd rather have fractions, but you don't have to, but I like fractions better. Raise it up 1 is negative 3, divide by negative 3, and then your plus c, and then put your u's back in. Now, I'm fine with you leaving that a negative power. That's fine. Okay? I'm fine with you just going like that and leaving it. If you want to flip that down to the bottom, that's fine, but a lot of times we do that and we screw it up. So you might be better off just leaving it just like that. But think about doing the derivative of that. Think about doing the derivative of that. You would bring the negative 3 down, which would cancel the negative 1/3. You would have this to the negative 4, which is what would be this. That'd be that on the bottom. And then times the derivative of the inside, which is 2x plus 3, which would be that part right there. Now, again, some of you are probably thinking this. For us to do these, they have to be kind of engineered and rigged to work, don't they? I mean, the ones that I give you to be u substitution ones have kind of been set up to work. Because what if that was a 2x squared plus 3 up there? Wouldn't work. It wouldn't work, right? U substitution wouldn't work. That's what I was telling you. There are a lot of functions that do not have antiderivatives, or at least fairly simple antiderivatives, okay? There are a lot of functions that don't, okay? Because how would there have to be? Think about it. We took all the elementary functions, products, multiplication, products, quotients, adding, subtracting, chain rule, all that stuff. We have rules for doing derivatives. So take any function you want to do the derivative to get this. To go backwards, if everything's going to have an antiderivative, that means every possible function had to somehow come out of the derivative formulas, and that's just not going to happen. You do a bunch of derivatives, you do these derivatives, and you get these antiderivatives, so you should go backward, but only with that set of antiderivatives that came out of the possible derivatives. Okay? And I can just give you a real easy one right here. Right here. This has no antiderivative equation. It just doesn't. There's nothing that when you do the derivative of it will give you that. So that's why we need this, right? Because if you graph this on your calculator, there would be a piece of area under that function from 0 to 4. There just would be. And unfortunately, Fundamental Theorem Part 2, as great as it is, isn't going to help us on that one. Okay? All right. So let's try a couple here. Try this one. Try this one. right, somebody got an answer they want to read?
4/3 plus x squared. 3 halves.
4/3, 1 plus x squared to the 3 halves plus c. Bingo. Okay? Okay? Because we're going to let u be the inside. 1 plus x squared. Why? Because we're thinking ahead. The du would be 2x dx. Now you might say, wait a minute, there's not a 2x dx, there's a 4x dx. The constants don't matter, right? We can move around. The 4 I can just pull out, right? I don't pull out the x, but I can pull out the 4. So I can pull out the 4, and when I do the du, if I get 2x dx, what can I do with that 2? Divide it over to make it a 1/2, right? So the constant, so if I'm looking for a match, the constant don't matter. Now, I say that, now on the last problem though, where we had 2x plus 3 on top, right? And that's what we wanted when we did the du of the bottom, the derivative of the bottom. Well, now that mattered because it was 2x plus 3. We couldn't get 4x plus 3 and then make that a match, right? We couldn't turn that 2x plus 3 into 4x plus 3. You can't do that, because of the plus sign. Okay, but here I can take care of that because it looks like this. So I say, okay, du is 2x dx, all right, and I'm going to move the 1/2 over. Now, I probably didn't know that right away, although I've done so many of them that I knew that was going to happen, but so eventually you get to that point. So you get to here and you think, okay, what do I got? Let's start subbing out. So you say, okay, I can sub that out. That's u to the 1/2, and I would write it 1/2 right away. I wouldn't write it square root of u. Why do that? Because you know you're going to do a power rule, so get it in a power right away. So that's going to be u to the 1/2. And then I see the x dx. That's the part I care about. X dx. And that's going to get replaced with a, and then that's when I decide I got to move that 2 over. So now the x dx is going to get replaced with a 1/2 and a du. And then the 4 is just hanging out there, so I just bring the 4 down. So the 4 is just hanging out there, and so I just bring the 4 down. Okay, just like I brought the square root down, the 1/2 power down. Okay, so the 4 comes down, and then the 1/2 got subbed in. So now when I do my power rule, 4 times 1/2, of course, is 2. And now I raise that up to 3 halves, divide by 3 halves, which means times by 2/3. Okay, and then that's where they got the 4/3 from. Okay, and that's where the 4/3 came from. Okay, so the fact that the derivative of the inside was 2x dx, and the du was 2x dx, and we had a 4x dx, that doesn't matter. That 4, we'll pull that out. That'll be fun. Okay, all right, try it out. Now notice this one's a definite integral, so on this one, you have to go farther. Once you find the antiderivative, then you need to plug in those numbers, okay, into your fundamental theorem part 2. But that's at the very end. So you do all the stuff we've been talking about first, and then you throw that in at the very end. And again, you want to compare answers, talk to each other, I'm fine with that.
Why you see that's not right. Jason, what do you make sure, Jason? Daniel, what you get to see, Johnny? So what is it? He knows that as well. Yeah. I'm talking about the first one, B minus A. That's B is the E value. E, I want to need so that's.
All right, what do we got? Anything?
0 minus yeah. Not 0 minus B values first.
You just want the, like the very end or just one?
Very end. Problem like this, right? I mean, because remember what we said, a definite integral, what's the answer? A number, right? So on a definite integral, the answer is a number. The antiderivative is how you go about getting the number. That's the big F of B minus big F of A. So to do that, you first need the antiderivative, right? An indefinite integral, when you don't have the 1 at the E in there, is just saying what's the antiderivative. The general antiderivative, you just tack on the plus C. Okay? Anybody getting a number? 1/4. 1/4 is the number. 1/4. What's LNE? LNE is 1.
Oh my God.
And LN1 is 0. Okay, so let's try it. So what are we going to pick for U? The inside, LNX, right? And again, thinking a step ahead, the reason you pick U to be LNX is the du, the derivative is 1 over x dx, which is setting right there. There's an x on the bottom, so there's a 1 over x dx right there. So it looks like this to start. U equals lnx. The du is 1 over x dx. Now we don't need bars when we go the derivative route. We never did before. Why is that? Well, because lnx is in our problem. So that means x can't be negative in this problem. Since lnx is a part of our function, x being negative is already thrown out of the domain. So we know x won't be negative. So when we do the derivative, it doesn't matter. Okay, so but when we go the other way, when you start with 1 over x, there's no restriction on x other than it can't be 0, right? So x could be negative. So when you do the antiderivative and get lnx, you've got to put the bars on it, and that's why. All right, anyway, when we sub out, there's our u, and so that would be u cubed. Okay, so that takes care of that part, is going to be u cubed. And then 1 over x dx is that part right there. Right? Not x dx, that's 1 over x dx, which is this. So we get u cubed du, which is simple. Then that's just 1/4 u to the 4th. Now, let's talk about something here. So once we get 1/4 u to the 4th, there's no need to put the plus c on, right? Because I'm about to do fundamental theorem part 2 here and subtract these, so we don't need the plus c, so I left that off. So it's 1/4 u to the 4th, but now so now you have an option. Once you get to 1/4 u to the 4th, you can either stay with u's or you can go back to x's. Because your final answer is just a number, right? Your final answer is just going to be a number. It's not going to have x's or u's. So how you get to that number is up to you at this point. You can either stay with u's or go back to x's. So now, I doubt that dawned on you to maybe go back to stay with U's because we've been going back to X's. So my guess is everybody went back to X's. So let me show you that first. So we take our U, which was ln x, and we put that back in. So we get 1/4 ln x to the 4th power. And then we do our right bracket, 1 to e, right? Because we just found big F. So now we plug in an e. ln e is 1. So 1/4 times 1 to the 4th, that'd be 1/4. Then we plug in a 1. ln 1 is 0. So that whole thing's 0. 1/4 minus 0 is 1/4. So that's how we get 1/4. Now, what was your other option? How could you stick with U's? Well, right here, we could have done this. We could have done this right here, except we can't put a 1 and an e here. Why not? Because those are x values. Think about this. This is a graph that has an area under it, right? That thing is a graph that has an area under it. And we're doing the area from x equals 1 to x equals e, right? Matter of fact, in the old days, the real old days, even before my day, I mean, we're talking real old days, you used to see integrals like this, x equals 1 and x equals e. They used to do that, okay? We don't do that anymore. But you got to understand that this number and this number are x values. X equals 1 to x equals e, we're looking at the area. Well, you can't use those with u then. You need u numbers. Well, if x is a 1, what is u? Just put a 1 right here for x. If this is an x, then stick it right there, and that'll give you the u that goes with it. So if x is a 1, you get ln 1 is 0, so u would be 0. If x is an e, put an e right there, ln e is 1, you get u as a 1. So you can put a 1 in there, and now you can go, okay, 1/4 minus 0 is 1/4. So now, it's 6 of one, half dozen the other. I mean, if you go back to x's, you're still going to have to plug an e into ln x, and you're going to have to plug a 1 into ln x, whether you do it there or you do it over here. It's really the same. So it does. I'm not sure it saves you work anywhere. It's just up to you how you want to do it. Okay, so if you want to, once you get your u antiderivative, if you want to go and put new numbers in there, u numbers, and then do your f of b minus f of a, that's fine. If you want to go back to x's and use the originals, that's fine too. Now, I think there's going to be a homework problem where they're going to ask you to change those. That's called changing the limits of integration. But you need to know about it because there are multiple choice questions on the AP test, like in our final, where they'll do this, and they'll say this integral is equivalent to, and then they'll give you a bunch of u integrals, right? And one of the u integrals would have been this, right? The correct answer would have been that. You know, A, B, C, D. And they say, okay, this would be the same as what? And they give you this whole list of u integrals. Well, you'll go through u substitution to see what it would be. So you're going to need to know about changing those limits of integration. Okay? And that's how you do it. You just take these x values, stick them in here, and change them to u values. All right. Let's try one more. Let's see. Yeah, that's a good one right there. Okay? Try that one. still right? All right, so it's about time now to get out of the super duper easy ones. Remember we talked about gateway, you got the easy ones and then the medium and then the hard, right? But so far we've just been super duper easy. Yeah, super duper, but right? So, but sometimes they get a little more involved, and usually the involvement is more algebra, but right, that's your U. Everybody pick that for you? Okay, well, good. And we got that much out of the way. We're getting to that part. Good. Now, your thought process might have been, geez, if I pick that to be 9 minus x squared, then the du is going to be negative 2x dx, and there's not an x dx setting there. There's an x cubed setting there. And that can be a problem, right? Now, remember, we did have the one earlier where we had extra x's, right? So what happens is, so your thought process on that one is, okay, I'm going to have negative 2x dx. There's an x dx setting there, but then there's extra x's. But we had a way to handle that, right? Kind of, before, and that one problem. Maybe that's what we do now. Okay, and it turns out that is what we do. So we get negative 2x dx, all right? And so then what we realize is that this integral could be thought of as a 3 out here. The x cubed could be thought of as this, right? And so what's going to happen is I've got this x dx right here. Now, of course, we know this negative 2 I can flip over here. So that negative 2, I can move that over to here as a negative 1/2. Okay, and that leaves me this x dx. And so now I'm looking at this integral. I'm thinking, okay, right there's an x dx. So I can get those out of there. I can get this out of there. That's going to be a u to the 1/2. The 3, of course, I can just bring down. So the only problem is I got this extra x squared there, right? Well, what could I do with that x squared? Comes back to this right here. What can I do to figure out what x squared is? X squared is what? 9 minus u. In other words, I could add the x squared over to this side, and I could subtract the u over to that side. And I got x squared is equal to 9 minus u. So that allows me to sub that out. Okay? Now, let's take a look at that then. So I think I've got them all there. I brought the 3 down. Okay? I brought the 3 down. I got this thing here is u to the 1/2. That's my square root u. I've got the negative 1/2 here, negative 1/2 du. So the negative 1/2 and the du replaced the x and the dx. So that took care of everything but the x squared. So x squared is 9 minus u, and I now have that. But this illustrates a really important concept. Again, it looks like I haven't made it any easier than the original. The whole goal is to make this easy. Well, remember the one we had earlier where you had x over x plus 1, and then we ended up with u minus 1 over u. Why was that easier? Single denominator, so we could split it apart. Well, here's why this one's easier. Our original problem is this. Now, could I distribute that through there? No, no way. You would never think of that. No. Why can't you? Because of the 1/2 out there. When you have a power outside of a sum, it's FOIL, and square root. You can't. And oh gosh, I hope we're all past this, where you would write 3 minus x here. I hope nobody thought of that. Okay, square root of this. You cannot square root the 9, square root the x squared. That's bad. Okay, we can't do that. And so there's nothing we can do when we have something and then we have this quantity to a power. We can't do anything. But look what we did. We've now turned it into the power is on a single thing. So by letting u be that quantity on the inside of the power, we've turned it into a u to the 1/2 times a 9 minus u, which we can distribute. So that's the advantage. We've turned it into something setting outside of a power parentheses into a single first power parentheses, and that's to our advantage because we can now distribute. And now we get 9u to the 1/2 minus u to the 3/2. Okay, on the inside here. Now I got a negative 3/2 out here. Okay, so I've got that negative 3/2 out in front. and I've got the 9u to the 1/2 minus u to the 3/2 inside. Now, I could leave the negative 3/2 out here and do my antiderivative, but then I'm going to get fractions in here, and then I'm going to have fractions on top of fractions, and so I'm going to go ahead and distribute. I don't always do this, but I'm going to go ahead and distribute that through there, okay? So if you come over to here, I'm going to go ahead and distribute that through there. Now notice I haven't done the antiderivative yet, so my integral symbol's still there. That's important, right? We talked about how when you do the antiderivative, that goes away. Well, I haven't done the antiderivative yet, so it needs to stay there. I've seen people do that. They get so caught up in all this algebra that they get to here and they think they're done. And they put the x's back in, and then they think they're done. And we haven't done the antiderivative, right? It's all just algebra. All right, so now I think I'm right so far with my algebra. Now we raise this up to 3/2 and divide by 3/2. Well, that'd be times it by 2/3. If I multiply this by 2/3, the 2's would cancel, 3 go into there, that'd be -9. If I raise this up to 5/2, I would multiply by 2/5, right? Raise that up to 5/2, multiply by 2/5. 2/5 times 3/2 would be 6/10. That'd be 3/5. So I'm going to get -9 u to the 3/2 plus 3/5 u to the 5/2 plus c. Now I did do my antiderivative, so now I take away the integral symbol. And then finally we put our 9 minus x squared back in for u. Don't forget that step, okay? And so, because if you forget that step, it's going to be wrong on the gateway test. Now if you're on like the 3rd gateway test and you make that mistake and it keeps you from passing, I might cut you a break, okay? But first one, you got to make sure, for sure you go back to those. Yeah.
Would this be like one of the last problems?
One of the hard, would this be under hard? I would say, yeah, I would say the fact that, there's an extra x squared, you had to get, yeah, probably. Between medium and hard, I would say.
It's hard thing.
Well, yeah, and then you add in the fractions. There's a lot of room to make mistakes because of the fractions, right? If it was one, because there very easily could be one, just a simple one that's a straight antiderivative power rule with fractions, and that causes people problems just because they mess up the fractions. You know what I mean? Now, I would call that an easy one, but this one adds the fractions plus that extra x, and it was not only an extra x, it was an extra x squared. You had to split the x cubed. So all of that together, I would say, make this on the hard end of the scale. Okay. All right. So, but it did point out an important concept where, how we use U substitution to turn it algebraically into something we could work with, where the previous one was not something we could work with. Okay. All right. So basically, it's a lot of practice at this point. So here's some problems in the book. I got 11 through 14. Then I just said pick at least 7 more. From 23 through 74, there's just a whole bunch in the book there, whole bunch of practice ones, so we'll come back to that page just like we did with the derivative page and just try some from those pages. There are some websites, they're not as good with the antiderivatives, I didn't think, as they were with the derivatives, but I'll show you those next week. And then the LH packet has a handful to try there as well. It's a fair number of problems, but number one, you have 3-day weekend, so you should be 3 times the amount of homework. Right?
No.
Again, it kind of goes back to what I said on the derivative test. And the numbers, are they as high that pass the first time? It's pretty close, but I would say it's a little less, possibly on this. And I think it has to do with how much time you put in. I think traditionally it's been a little less, but I think traditionally it's February and seniors, I don't know, as we get towards February or March or whatever, we maybe don't put as much time as we need to. So juniors ought to be fine, but the seniors, whatever. It's how much you put into it, how much work you do, how many you practice. So that's going to be the key. That's going to be the key, right? All right, you can work the rest of the time here.
Oh, it slid off.
Oh, it's on my last week.